today we'll be talking, and then today I'll be talking about some topics related to divide and conquer, which is a very common problem-solving paradigm in theoretical computer science. So if everyone's fine, we'll jump into the material at this time. So also, if you're like lost at any time or anything, you can always like just jump in and correct me or like ask me a question. And also it'd be nice if like people were to participate today because I want to make this like pretty interactive. So with that said, let's do like a simple problem first. So given this is our first simple problem for the day. So what we want to when I say we want to find 2n, what I mean is that we actually want to like evaluate 2 to the n in let's say like decimal representation. Also, what I mean is that I want to like minimize the amount of time it takes to find this. So, first, can anyone tell me like a very obvious way to find this?
Multiplying 2n times.
Yeah. So you can so you do 2 times 2 times 2. Right. So this takes n multiplications. And let's say n is something like 1 billion or 2 billion or 3 billion. We're also going to assume that like we have memory enough to hold the result of this. Um, you can, if you don't want to assume, make that assumption. You can also just like say that we want to find this 2 to the n mod some large prime. So you want to find 2 to the n mod some prime like 10 to the 9 plus 7. But for ease of like conceptualization, we'll just pretend that we have enough memory to store the result of this. But yeah, if we want to do this in a slow manner, you can just multiply 2 n times and you get the result. Now, it turns out that you can make this much, much faster. Um, so does anyone have any more ideas for like some way to like speed this up? Also, if you've seen this before, don't try not to spoil it if you've seen this before, by the way. I promise it'll get harder in like a couple minutes
Like
because we'll do
if,
like a challenge. Yeah.
if like n is even, we can multiply 4n by 2 times. That's like faster, I think.
Yeah, this is good. So, so 2 to the n equals 4 to the n by 2. So, since we don't want to deal with halves, um, there's like some detail with like the exponent mod 2. So, what we do to deal with that is this. So, 2 to the 2k equals 4 to the k. And then 2 to the 2k plus 1 is 2 times 2 to the 2k, which is 2 times 4 to the k. So in either case, we can divide the exponent by 2. So now this is actually the key insight. So with this, um, we can actually find the result. What I was like iterate this trick over and over again. Does anyone want to tell me like what would happen if I kept doing this? The same kind of like having the exponent thing.
It basically turns into multiply 2 to the power n minus 1 2 times.
It's not n minus 1 actually. That's close, but it's not. It's not 2 to the n minus 1. Uh, Instead, like think of like what you're doing to the exponent each time you like apply this operation.
Or dividing by half.
Yeah, so you're dividing the exponent by 2. So like roughly like what you're doing is like this. So you're doing a to the n equals a to the n by 2 to the power of 2, which is equal to a squared to the power of n by 2, right? So I'm saying if you start with 2 to the n, and then first you do this with 2, so you replace the 2 with the 4. Then again you do this with 4, you replace the 4 with the 16. You can keep doing this. So as you like iterate along, um, can you tell me like what would happen to the exponent at each stage of the process?
We'll keep halving the exponent.
Right, so how many steps will it take for the exponent to reach 1 in this case?
Log n.
Right. So now we actually have a fast algorithm. So let me first like illustrate an example of this, and I'll show how it generalizes. So let's say like 2 to the 7. This is 2 to the 3 times 2 plus 1. So it's 2 times 3, sorry. And then now you can evaluate this to just be 128. So the other way to see like what happens in this process is like at some stage we'll get to like just 3 numbers multiplied by each other, and there's no more recursion going on. So at this stage we can say that if like n equals, or you can also just observe that if 7 equals 1 plus 2 plus 2 squared, then what we're finding is 2 to the 1 times 2 to the 2 times 2 to the 2 to the 2. And you can find this just by iteratively squaring. So in general, um, to the n goes to uh, so in general, what we do is that at each stage we have the exponent square it and then multiply by the remainder. So time log n steps for exponent to each one. Not floor, just log. So we'd say that the algorithm is O of log n. So does everyone follow where we are so far? Because just like, yeah, if you could all just like, if few of you could just say, if you have any questions, you could just speak up. That would be nice.
Oh, can you just explain briefly what O of login means?
Sure. Okay. This roughly means that like the running time for the if we say that like in for general n, the algorithm would take So we say that algorithm is f of n steps in general, then O of log n implies that like for some like absolute constant c, we have f of n is less than or equal to c log n. So what this means is that like the function's like running time is bounded above by c by some multiple of log n, which means that like the growth rate of the function on the left, the growth rate of the number of steps an algorithm takes is c log n, is like proportional to logarithm of n. Does that make sense?
Yeah. Okay.
Okay. Yeah. Any other questions?
No, I guess.
Okay. So I guess if everyone's clear, like we can move to like the actual like meat of today's talk, which is that we want to solve this problem. So I will first just screen share the problem, or rather I'll just write the problem down for everyone, and then after that I'll give everyone like a couple, like 5-10 minutes to work on it, and then we can like start building up the solution like one by one. So the number we start with the number n equals 1. So at any stage we choose a positive number, or okay, d is positive here clearly. We choose the number d divides n, and then take n to d plus 1 times n. So find a sequence of steps after which 2021, the 2021, the 2021 minus 1 divides n. So we want an algorithm after which this big number will divide n. So let me just like give like an example like the operation we want to do. So for example, one sequence of stages, if I start with 1, then the first step is fixed because the only divisor of 1 is 1. So 1 goes to 2. Then I can pick 2 divides 1. 2 divides 1, so you multiply by 2 plus 1, which is 3. So it goes to 6. Then you again multiply by, so for 6, we can multiply by, say, 3 plus 1, which is 4. You get to 24. And then you can kind of see how this would progress. So we want to, of course, minimize, since this is like a talk about like optimization and theoretical CS, we want to minimize the number of steps. And okay, to give credit where it's due, this problem is from CMI&C 2021. And yeah, shameless plug. This will be online this year, so you guys are all encouraged to take this test. But anyways, so I want to minimize the number of steps, and I'll just give you like a couple constants to aim for, to like do this. So for like first step, try to get okay, say the number of steps is k. I'll give you like a couple bounds for like a couple like number of step, like a couple step, like k to aim for. So like try to find some algorithm which takes only these many steps. So the first step is like anything at all. So okay, this is just like k is less than infinity. Like just find any algorithm that works. The next step is find something that works in this many steps. Then try so these are the first five. These are the first four uh tasks, and if we have time after, we'll move into like some even like lower values. But first, everyone can have maybe like 5-10 minutes to work on this. Yeah. Any questions about the problem? Then please let me know. But is everyone on the same page?
Yeah, it's
Okay. So just try for the next 5 to 10 minutes to like figure out some like solution for each of these different like for try to like hit these values. There's like increasing in difficulty, and try to hit some of them. Yeah.
So the second one should be easy. You just go from 1 to 2 and then 3 and then 4 and so on.
Right. Okay, that's correct. So for the second one, so the first one is like kind of the first one and the second one are kind of equivalent because like the most obvious possible algorithm is just the second one. So with this, it's like you go from 1 to 2, and then this is the divisor 1. You use divisor 2 to get to 2 times 3, 6. Then you go to divisor 6 to get sorry, no. Use divisor 3 to get 4 factorial, and then 5 factorial, etc. until like n factorial. And what follows, let's just denote this like number as n. So yeah, in n steps, what you can do is you just keep multiplying by like 1, then 2, then 3 until up till n. And at each step, the number you have is n factorial, and then the next number is n plus 1 factorial. So this is like a nice solution because like, or not nice, it's like a solution because it tells us that like we can at least get like factorials and things like that. But it turns out that like, or like the thing that we have to know is that like there's a lot of work that we're like wasting here because like basically for any number that doesn't divide 2021, so any number that doesn't divide like 43 or 47 is like wasted work. Like multiplying by 2 does nothing for us. 3 does nothing for us. There's so much stuff that we're doing that like we don't need to do. So in the remainder of the solution, what we're going to try to do is just kind of cut down on as much like unnecessary work as possible. So let's first like start with something like let's try to do something like somewhat simple for the second one. We'll do the second one together, and after that, I'll give you guys some time to try the third one. So we want to go from like n steps to 10 to the 10 to the 4 steps. So the idea is that like as hinted before, like what we want to do is use binary or use some sort of divide and conquer mechanism. So let's sort of like play around a bit. Let's say we want to get to like 100. Um, to make this like as interactive as possible, let's just try to get to 100 with as few steps as possible. Starting at 1. So does anyone like, or okay, the first move is 2 automatically. The second move, after the second move, we have like choices. So does anyone want to like give me a move to make here? Like we'll try to get this together with like a number divisible 100.
I think we should pick 3 here.
Yeah.
Take so 2 divides 2, so we take 3. Okay, so you get to 6. Then
4.
4, yeah.
okay, sure. So then you multiply by 5, so it's 30.
Yes. And then 6.
How exactly we multiplying by 5?
Oh yeah, we can't multiply by 5.
Oh, yeah, because 4 does not divide 6.
Yeah.
So, what I meant is pick 3 and then multiply by 4.
Yeah.
Okay, yeah. And then
Pick 4 and multiply by 5.
okay, I mean
would
you
be
can
120.
keep going like this, and then we'll get to like n factorial. Also, whoever is if you're not talking, like please mute because I think the echo is there, but it's not. So yeah, I think this is like doing the n factorial thing. But can you guys see like by multiplying by 3, for example, like we could keep trying this, but the thing is that there's a lot of like things that we're multiplying by which are like somewhat unnecessary.
We can go
So
to
let's
1, 2.
try to-
Yeah, we can go to
Sorry?
1, 2, and then, I mean, you can multiply by 2 again, and then 5, and then you can get it directly from there.
Yeah, that's very
It's
good.
like
So
we can go 1, 2, and 1, 2, 6, and then 18, and then 7 multiplied. But that will
So
also
1,
exceed
2,
100.
saying 1, 2, 6, 12, and then you multiply by 5 because we have 4 divides 12. So then that's 60. And you multiply by 5
Yeah,
again
this
because
is
5 still
this looks
divides.
good. This looks more good.
Why don't we just go 1, 2, 4, 20, 100?
Yeah, that's even better. Wait, we can't go 4.
Why
Because,
not?
Because 1 divides 2.
Oh yeah, we can go.
oh, right, okay, yeah. Yeah, okay, yeah, this works. So, like, what we can see from here is that we sort of, like, used 4s to create 5s. Because to get the 5, we used, like, 4 divides n to multiply by 5, and then we just finished with that. So, this is, like, something that this is something that's useful to know. So, if p minus 1 divides n, then we can go to p divides pn. Sorry, so this means that like it's useful to have multiples of p minus 1 lying around just so that like that'll like make it easier for us to do things. But also like we would like to be able to do something like even more general. So the next thing that we'll try to do is like go from p to the k minus 1 divides n to p to the k divides n. This is, but we'll get to that soon. So where you can go from p minus 1 divides n to p minus 1 times p divides n. So just keep this in mind for like future.
Previously we go to 100 from 1. So what will we do now?
No, we did 100 just to see like what kind of
Yeah, like
structures
what's
we
going
can
on?
kind of play with. Yeah.
Yeah.
Okay. Okay. So like
Can you
what if we
explain the
want to get to
third one once?
Oh yeah, we'll get to that. We're going to get to that. So now for the next thing, the insight is like we can represent any so what we kind of just figured out is that there's only like some primes that we care about. I mean, you can only get those primes. So now, like let's say we wanted to just build up some prime. So you wanted to build to say like 43 because by the way 2021 is 43 times 47. So the primes that are important to us are just 43s and 47s. But to build to 43, does anyone have like an idea on how we can like build just to that?
First build to 42 and
Yeah, okay, good. So
you can go 1, 2, 6, 42, 43.
yeah, that's good.
Oh, so this like 0 divides 42 is 0 plus 1 times 42.
I think also the last number should be 43 into 42, right?
Right, yeah. Thanks. Okay. So like what about if we wanted to go to 47? To go to oh yeah, whoever's gonna go to 47. Anyone want to try?
Yeah, so if we multiply 4 and then
Okay.
8.
Okay. This is what you were saying, by the way, you go 1, 2, 4, 8.
Yeah.
Okay. And then
So like this is we will get 48 but not 47. So
yeah.
and then 40 from 48 we cannot go to 47. So like this does not work.
Okay, so the good thing to notice before
One,
yeah.
2, 4, then 4 times 5, Looks like 4 times 10, then 4 times 10 into 11. Okay, this is then 20 into 11. Like 10 into, then 20 into 11 into 23.
Okay, that's nice.
Yes. Then 46 multiplied by 46 and then multiply by 47.
Yeah, and then you can multiply this by 47.
Yeah.
Okay, yeah. So, these.
But what is this? How this worked?
Oh, sure. So start at
Like
one.
what we are trying to reach?
This is just to reach 47,
Like
or
last
multiple
number should be
47 rather.
so last number would be 47.
No, divisible by 47. So it's just
Oh, okay.
something divisible by 47. Yeah.
Okay.
Okay. So the idea is that like we want to get to like a prime. We want to make the number like larger as fast as possible, so that we can reach it faster. So I'll just say like how to do the primes in general. It's like the idea is like not too crazy after what we discussed. Yeah. So the idea is to take the prime p and like write it in binary. Right? Then now just note the following. Start at 1, you multiply by 2, and then at any stage you can multiply by 2, by the way. Because like 1 always divides any number. So you can always double. So first, we multiply like n naught minus 1 times, and you get like 2 to the n naught. Then you multiply again by like you multiply 2 to the n naught plus 1. Sorry. You multiply 2 to the n naught plus 1. Okay, wait, this is bad. My bad. Okay, so I'll just write this in like recursive form. So, first, if we say like we need t steps to get to 2 to the n, or to get to some like n, or sorry, say we have like f of n steps to get to n, then we have f of 2n is less than or equal to f of n plus 1. Claim that this is true. Since 1 is always a divisor, like from f of n, you can always multiply by 2 to just get to f of 2n. This is fine?
What does f the function represent? Oh yeah, okay. So this is fine.
Yeah.
So that's less than equal to, right?
So this just implies that
f of 2n is less than equal to f of n plus 1.
I meant to write n to 2n like this. So this is what we have. Now like in particular, like if we write p in binary,
Oh, how did you say
first
this?
just divide by
Less than-
2. Just keep dividing by 2 until. My bad. This is also a typo, sorry. So explicitly speaking with p, like we have like f of p is less than or equal to like f of my bad. And then just keep going down. So basically in each stage, If it's a multiple of 2, we divide 2, and then a multiple of 1, we subtract 1. That's basically what we're doing. In terms of like binary, if we look at it that way. So this recurrence gives us that like this just implies that like f of m is less than or equal to 2 log 2 of m by induction, actually. So I'll just show this explicitly, I guess. Yeah. So so basically, like, just induct f of 1 is 0, and then f of 1 is 0, f of 2 is 1. So then you can just like continue with the chain of inequalities just using this, and that implies that we have this result. Now, just for n, we have f of n is equal to 2 log 2n. And then you can just estimate log 2 of n. It's like approximately something like on the order of 10 to the like 8084 or whatever. Like, it's something that's less, it'll be like, you'll get something that's like certainly like less than 10 to the 10 to the 4. Just if you just estimate the constant. I want to do that just because like it's kind of like boring details. And if you want, you can like work out this part later. But yeah, so that's how we do 10 to the 10 to the 4.
Oh, can you conclude less than equal to 10?
Sorry?
Oh, did you get that n is
Can you
less
repeat the question, please?
log 2n? Oh, how did you get of n?
How do you get the f of m is less than or equal to 2 log 2m?
Yes.
Sorry? Okay, yeah. It's just that like
Yeah.
f of 2m here. Okay, so f of 2m from if like we have that like 2 times the log 2 of 2n is less than or equal to 2 times the log 2 of n plus 1. If you subtract, that's like equivalent to like, oh, sorry, wait. Right, yeah. So, like, okay, if we just look at this f of 2n less equal to f of 2n less equals f of n plus 1, then the idea is I'll just write down the algorithm for you. So to get to say like, I'll just show you how this like double step will imply that we can get into 2 log 2m steps. So let's just take like p equals like 2 to the 3. Actually, it's not even prime, but it doesn't really matter because the algorithm is the same. So 2q plus 2 to the 5th. What we'll do is like, you'll go, first we'll go from like 1 to, we can just go from 1 to 8 directly in 3 steps by multiplying by 2 3 times. And then now we need a number divisible by 1 plus 2 to the 5, because like this 8 will continue to divide it. So we need to get to a number divisible by, that divides 1 plus 2 to the 5. So then, again, we multiply this 8 by 2.
Oh, don't we want 1 plus 2 square? I guess.
Right, yeah, my bad.
Instead of 1 plus 2 to the power 5.
So you go 8. Yeah. My mistake. So we go 8. Then you go we multiply by 2, and we multiply by 2 again, and then you just multiply. So, like, the idea is just that like in each step, we're just building up one component of the binary thing. Sorry?
But you can do this directly in one step also, no? Like 8 already has 4. So 8 into 5.
Yeah, in this case we can. But if we have if the binary blocks get increase very fast, we'll need to build up extra ones or something. Like, yeah. Like, suppose that we had something like 2 cubed. It's we can make minor optimizations here, but that's a property of the numbers 3 and 5. Like, in general, this is kind of the best we can do so far with this strategy. Like, if I had something like 2 cubed plus 2 to the 7, then first we need to go to 2 cubed, and then from 2 cubed we need to go to 2 to the 4th. Sorry. Like, we have to do this. Because we need, the gap between 7 and 3 is 4. So, it depends on the gap between the exponents. So that's what I'm saying, it's property of the number, the fact that 5 minus 3 is less than 3, basically. But, basically, to get this inequality that f of m is less than or equal to 2 log 2 of m, if we have, if we just say that, n equals 2 to the n1 plus 2 to the n2 plus, so 2 to the n k for some k, then, there's n1 times, for at least n1 times, we need to first build up to 2 to the n1, so that takes n1 steps to double. And then there's in the while we're doubling, we have to do p minus 1, or sorry, not p. So we have n, so we first get to n1, so n1 steps to get to 2 to the n1, then k minus 1 steps to get each bit, so we just build up bit by bit, and then this is enough to get us n1 plus k minus 1 step algorithm. And that is enough to give us this bound of 2 log 2 of m. That's just because n1 is less than log 2 of m by construction, and then k is also less than log 2 of m clearly. So the bound is bad, but it's enough for us. Does that make sense?
Yes.
Okay, good. So now let's move on more. So the next step, so this step we can kind of get just through binary. So the next step to get it'll take some more work. We'll have to do some we'll have to make one big observation. So yeah, let's get to that. Sorry, not 4. I'll rest it to the 10. Okay, so for this, I'll just give I'll give a hint, and then I'll give a hint. It'll use 5 minutes to try, just based on the binary idea. So in the previous step, so we use binary on element is just n. So we use binary on n itself. So now say we want to get a number divisible by n to the power of a. see if you use binary on a itself. So like in this case, like you're doing some sort of like logarithmic thing on the exponent, and then like the reason that this would be good is because like to get to n, take like some constant number of steps, say like so, or to get to like some small n, you'll get like some small number of steps, and from there, see if you can use like binary on a to get to like some power of n, and like getting powers is like the power, like the thing that we want to do. So see if you can use binary on the exponent itself. Yeah, that's like the hint that I'll give you guys. And then I'll give you guys 5 minutes to try, and then we can come back. Okay. So has anyone made any progress?
Yeah, we can just apply the same idea. So we can go from n. Once we get to n, we can go to n square, and then we can go
Yeah.
to n to the power 2 to the power k, or k plus 1, and then we can go to n to the power 2 to the power k plus 1. Like we can basically do the same thing, because just like how we can multiply by 2, we can always square. So
How can we? Okay, yeah, sure. Right. Okay, that's sort of like that. That's the basic idea. So, let me like kind of make this clear, like make this explicit. So, say we have some x. Then if we are like, let's say we have like x minus 1 times x actually. Like, if x is prime, okay, I should just use primes at this point because like we're kind of just handling primes individually. So, say we have like some p minus 1 times p, right? Then like, okay, first if we have p, then we have to have p minus 1 also, because like the only way to get a multiple of p is to multiply by something, where if you add, then you get a multiple. Okay, so I guess like you have some kp minus 1, but we'll just say we have p minus 1 just for like ease of argument. So if we have p minus 1 times p, then the first thing to note is that we also have p minus 1 times p plus 1. So this means that we can multiply by p squared, actually. Then if we have p squared, then again we can repeat the argument, and we have like p squared plus 1 times p squared minus 1 times p squared times p. So then this means that we have like p to the 4th minus 1 p squared p. So we have p to the 4th p squared p 4th minus 1. And it turns out that we can just continue along like this. So what we get is that like in each step we can like double the exponent, basically. Double the exponent of p. Right, yeah. You also just like, this is the same thing as like interstellarly squaring, but noting this is useful for like the next step, because like we need to be able to get like even larger values of exponent quickly. So I just wrote down the p minus 1 thing just to like kind of like prime you guys for the next step. But yeah, what someone is saying about saying like p, and then you go p squared, then you go p to the 4, and then you go p to the and then you go p to the 8, then you go etc. until p to the 2 to the k. This is like also equivalent. It's like a constant factor better than what I was saying earlier as well. It's just that this thing is like the next step that we're going to do. So if we start with p and we can iteratively square, this means that if we get to 2021 to the 2021 to the 2021, first we need to get to like the base primes for 2021. So these are 43 and 47. Right. And then for now, let's just like kind of just do the 43 part. Oh wait, this is wrong, by the way. So it's 43, we can just keep squaring. So 43 to get to 43 will like take some like constant number of steps. I think like what we had earlier will give us like by this we can do it in like 4 steps. Yeah. So 4 steps to get to 43, and then like log 2 the exponent times. I guess it's ceiling of log because like we need the exponent to be larger. So 4 plus log 2 2021 to the power of 2021 to get to 43 to this power. Fine. So now this log 2 of 2021 to the power of 2021 is like around, or it is equal to like 21 log 2 times what, 11. It's like less than this. So it's less than 4 plus 2021 times 11. And then to get 47, how many steps did we have earlier? So yeah, we had 6 steps earlier. I don't think it matters too much, just as long as it's like a small number. And then again, the exponent will be the same. So it's like 6 plus 2021 times 11. So overall, the sum is like, which is definitely less than 10 to the power of 10. So that handles this case. Okay, yeah. Now that we're like close, and I also give you the hint with the p minus 1 p and like trying to raise powers with this, I want you guys to try to like look at things like p to the a minus 1 times p to the b, because that will like let us optimize even more. So yeah. I'll give you guys like a couple minutes just to try to see what you can do with these kinds of numbers. And I'm leaving this like very open-ended now. Just because like the last step is like kind of like very how do I say this? It's like one idea, so I don't want to like give away too much. So I'll just say like look at numbers of the form p to the a minus 1 times p to the b and see where we can push that. Yeah. Also this is like, yeah, so what we have so far is like already very strong. So now just try to like decrease even more by looking at these kinds of things. So I guess we'll like reconvene fairly soon.
I have a doubt. In the original question, we want the number to be divisible by 2021 to the power 2021 to the power 2021 minus 1.
Yeah.
So you didn't include the minus 1, I guess.
Oh, that's right. But okay, yeah, that's actually right. Okay, yeah, but for that, we just do like, if we just do this algorithm that I had above. Sorry, I completely messed up. My bad. So okay, I'll just show how to get this thing. Right. Okay. So the idea I was saying was that when we have p and p minus 1, then we can go from that to like p times p minus 1 times p plus 1, which is p times p squared minus 1. And then from here we can go after two steps, by multiplying by p squared and then p squared plus 1, we can go to the p to the 4th minus 1 times p times whatever p squared. And then after two more steps, we can add 1 to this. So we can get p to the 4th plus 1, p to the 4th minus 1, p squared, p 4th. Then continue along. And at each stage, we have like, so we go from p minus 1 to p squared minus 1 to p to the 4th minus 1 to p to like 2 to the n minus 1. Because in each step, what we're doing is we're taking like the difference of squares for one exponent higher and then pushing it through. So Yeah, so we go from p minus 1 to p squared minus 1 to p to the fourth minus 1, etc. until p to the 2 to the n minus 1. And then at each stage, it takes 2 steps to move to the next one. Right. So first we do p minus 1, then after each 2 steps increases by 1. And now, again, we can like bound it by like 2 log 2 of the exponent to get from p minus 1 dividing to p to the 2 to the n minus 1 dividing. So what we had before still works. It's just like off by a factor of 2. So now again, we have to look at the initial conditions for 43 and 47. So it's 43. It takes like 5 steps or 4 steps. Then now from 42 to 43, we go to like some big power minus 1, or not even. Sorry, this is again wrong. So it takes 4 steps to get to 42 times 43. Then again, we get 47 in like 5 steps. And then also like you could get so like the point is that we can get 2020 times 2021 in some small number of steps. By small number, I mean like, let's say like under 30. Like under 30, certainly you can do. Even just by like, even if we just use like our old algorithm, like we can get like log of this. So, and log of this is like less than 22. So like we can get like less than 30 for sure. So say we have 2020 times 2021. Then from here, we can just now go 2021 minus 1. So this has 2021 minus 1. Then you go 2021 minus 1, square minus 1. Then, sorry, not cubed. Fourth minus 1. So now again, in each step from here, it takes 2 steps to move to the next stage. Because in 2021 minus 1, we first have to add 2 twice. So we go 2021 minus 1 times 2020 times 2020 plus times 2021 minus 1 times 2021, and then times 2021 plus 1. So we get 2021 squared minus 1 this way. Then again, do 2 steps on 2021 squared minus 1. So we get 2021 squared minus 1 times 2021 squared times 2021 squared plus 1. Then you multiply the 2 together and you get 2021 to the power 4 minus 1. So now if we just keep iterating, we'll eventually get like 2021 to the big power minus 1. And then like once we get to like some sufficiently big power of 2021, we need to like get some, we just have to get, sorry, just 1 second. Let me just check my notes really quick. Okay, yeah, my bad. So I will just show the solution to this like from start again. Sorry for all the like mistakes and stuff. It's kind of bad, but okay. So the idea is this. So what we want to do is we need to get 2021 to the power of 2021 to the power of 2021 minus 1. So first we start off with 2021 minus 1 times 2021. So up till here is fine. And then now, first I'll just show you how to like raise it. I'll show you how to like raise this power iteratively in just the left side. So first, so first you get to 2021 to the power of 2 minus 1 times 2021. And then this is equal to 2021 to the power of 3, or okay, that's actually not relevant. So we have to like introduce some new notation for this. The notation will just make it like a little bit easier to understand. So say that we have x to the a times x to the b minus 1 for some x. Then I'll show how to like increase the a and the b. So say it takes g of a comma b steps to get So say it takes g of a to b steps to get x to the a times x to the b minus 1. Then what we're going to do is we'll find something with b equals 2021 to the power 2021 and x equals 2021, and that'll give us a result. So that's the strategy. That's what I was saying before with like p to the a times p to the b minus 1. So for g of a b steps to get here, I'll first try to increase this fast. So say you have g of a b, then I can take this to g of a b plus d for any d that divides b. So like what I'm saying is that from g of a b, from like if we have x to the a times x to the b minus 1, we can go to x to the a times x to the b plus d minus 1. So roughly speaking, how we do this is the following. So say we have x to the a, x to the b minus 1. Then since d divides b, we have x to the d minus 1 divides x to the b minus 1. Now we do the following step. So x to the d times x to the b minus 1 over x to the d minus 1. So if we start with something, some like some m. So you go m to x to the d minus 1 times x to the b minus 1 over x to the d minus 1. Where this is like a divisor of our initial number. So you multiply by that, and then we have this x to the d minus 1 in the denominator of the second part. So we move it to the beginning. And this is just like by identity. So what we're doing is like we just rearrange. So we have like some m for which x to the a times x to the b minus 1 is a divisor. Then you multiply by x to the d over times x to the b minus 1 over x to the d minus 1. Since b divides d, or since d divides b, and x to the b minus 1 divides m as well, by rearrangement we can get this. Right. So like this gives us a way to get like new divisors from old ones in small, so we can continually raise what we have. So now for the bound of 10 to the power of 10, we have first we have this lemma, which is that like we can step from g of ab to g of a b plus d for any d dividing b. So we have this, first we have this bound. So this is what this is saying is that g of a b plus d is less than or equal to g of a b plus 1. Is that clear so far?
Yeah.
Okay. Also, there's a small typo here, by the way. I meant to write so we go from m. So since x to the a x minus x to the b minus 1 divides m, we have m times x to the d x to the b minus 1 over x to the d minus 1. And that's just because x to the d minus 1 also divides this. And then when we do this thing, the inner part is x to the d plus b minus x to the d over x to the d minus 1 plus 1. And that's equal to the x to the d plus b minus x to the d plus x to the d minus 1 over x to the d minus 1. And the reason we multiply by this thing is just because we have a factor of x to the d, x to the b minus 1. Oh, we're also assuming here that a is greater than or equal to d, by the way. So we have x to the d, x to the b minus 1 as a divisor. And that means that since x to the d minus 1 is a divisor of this divisor, is a divisor of the whole thing. So we have a divisor x to the d, x to the b minus 1 over x to the d minus 1 plus 1. And now by rearrangement, it becomes x to the b plus d minus 1 over x to the d minus 1 times x, or times m. And now this d minus 1 can just go to the other side, so we have x to the b plus d minus 1 as a divisor. And our a is preserved, of course. Like, we didn't do anything that affects, we never divided by any factors of x. So we're divisible by at least that many factors of x. So we still have an x to the a. So that proves this inequality. Then now the other inequality that is useful for us.
I have one doubt here.
Yeah, sure.
Oh, yeah. So here, how did you get x to the power d into x to the power b minus 1 upon x to the power d minus 1 plus 1? Like, I got x to the power d minus 1 divides that.
In which one?
Oh, like, I got this x to the power d minus 1 divided x to the power b minus 1. From that, how did you get this?
Which one?
Like, n to n times x to the power d into x to the power b minus 1 upon x to the power d minus 1 plus 1.
So x power d times x power b minus 1 over x power d minus 1 plus 1. You're asking like how I got this expression? Okay, yeah. So what we know is that x to the a, x to the b minus 1 divides m, right? This is like our standing assumption. Like, we're assuming this is true so far.
Yeah.
Okay, so then from here, x to the d minus 1 divides x to the b minus 1. Because d is a divisor of b, right?
Yeah.
Then also we assume that a is at least d. So then that means that x to the d divides x to the a, right?
Yes.
Okay. So now, what all this implies is that like x to the d times x to the b minus 1 we have x to the a, x to the b minus 1. So we can divide this by x to the b minus 1. Sorry, x to the d minus 1. Since x to the d minus 1 divides x to the b minus 1, this is still integer, right?
Yes.
And then also we can divide by x to the power of like d minus a. Sorry, x to a minus d. A minus d is still positive since a is at least d. So then when we divide, this a minus d will go up and we'll get x to the d in top. So that's how we get this divisor of m. So this number divides m. Right.
Yeah, got it.
Right, and then now, since this number divides m, we can add 1 to that and then multiply.
Yeah, got it.
Right, yeah. Yeah, so I'm sorry to everyone if like that was like confusing. It's like I just messed up like multiple times. I just made like a bunch of small mistakes so that carried over. And yeah, so my bad. But this is how we can get from x to the power of a, x to the power of b minus 1 to x to the power of a, x to the power of b plus d minus 1. Then now we have one more thing, this g notation, that's useful for us. So we claim that this is also true. Yeah, this is like basically just saying that if we have something, then we can like multiply both the base. We can multiply both of the exponents by something. In one of them, we're adding, the other one we're multiplying. So the reason for this is the following. So if x minus 1 divides n, then clearly we can go from x minus 1 to x to the power of c minus 1 like pretty fast. And the way you do this is just the following. So you have x minus 1, then you have x, then, okay, in a couple of steps, you can get to like,
The binary idea, basically, right?
yeah,
Or
just the
that
binary
is-
idea. Yeah. Just like we already know how we can do this. We can do this in like, we can do this fairly fast in like C steps or whatever. But yeah, basically, like we can build from x minus 1. In C steps, we can build, sorry, not C steps. This is just strictly G of OC, like by definition. And then now x to the
What's
C.
O here?
0, sorry, 0.
Oh.
Yeah. X to the CA, x to the CB minus 1 is now equal to x to the C, the power of A, times x to the C times B minus 1. So basically like we have, if we have x, this is like x to the C to the power of A times x to the power of C to the power of B minus 1. And then now we already have x to the C minus 1. And then to go from here to there, this is like from going to from G of 0, 0 to going to G of AB, where now we're replacing with that. Is that clear? Like basically for G of AB, we're working with x to the power of A and x to the power of B. Now instead of working with x to the power of, we're just working with x to the power of A, x to the power of B. Now instead of doing that, instead of working with x, we're working with x to the power of C itself. It's like we're powering C before we do all this exponentiation stuff. So yeah, we have this x to the power of, we have this x to C to the A times x to the power of x to C to the B minus 1. And then this will take an extra G of AB step. So basically the idea is that we have this inequality now. So is that clear?
Yeah.
Okay, cool. So now I'll just show how to get the bound of 10 to the 10. And I think that might be like most of the time that we have for today. I'll try to show one more thing, but I don't know if we'll have the time. But yeah. So now, first, so the idea is to prove that like G of 0 is equal to m first. So what we'll do is first we'll get to like 2021 to the power of 2021 minus 1.
Sorry for this, Kevin. Can you just show
Yeah.
the definition of G once more?
Sure. I'll just define it one more time for you. So G of AB is the minimum So okay, this is like I'm not right with the intention. I'll say with words. So the way to think of G is that say we have x to the a. Say that we have x minus one. So from x minus one, it's the minimum number of steps to build x to the a times x to the b minus one. Is that clear?
Yeah, got it.
Yeah. So the previous inequality is, I'll just go over that one more time. So in x, to go from x minus one to x to c minus one is by definition g of 0c. And then to go from x to c minus one to x to the x to c to the power of a times x to the power of c to the power of b minus one is definition g of ab. So this means that that this inequality g of ca, g of ca, cb plus equals g of ab plus g of 0c is true. So that's this inequality. And the previous inequality is just like if we have x to the power of a, x to the power of b minus one, in one step we can add d to the second exponent without doing any harm. So that's that step. So that's why these two inequalities are true. And now we'll apply to like the problem at hand. So the idea of what we want to do is now this. So first we want to get to 2021 to the power of 2021 minus 1. Then 2021 times we'll use the above operation to multiply this 2021 by 1. We'll multiply this exponent by 2021. Because like that's what the second lemma allows us to do. So we'll multiply this thing by 2021. We'll multiply the exponent by 2021 to like raise that power. So first we use the base and we get the exponent. Then again we apply the operation of the exponent to get up. So let me show how to do this. So first we know that like g of 1 comma 1 is 1. Because if you have x minus 1, then to get to x times x minus 1 takes one step. So this is definition. Then also, then this just implies that like from g of 1, 1, you can go like g of 1 to in 2021 steps because like in 2020 steps because like the first operation allows us to add a divisor to the second argument. So from 1, 1 we can go from to 1, 2 plus 1. They go to 1, 2, 1, 1 plus 1, then 2 plus 1, then 3 plus 1 until 1, 2021. So this is like, this allows us to get there. And then also now we have, this is what we want, by the way. So we have g of 0 from 2021 is now less than equal to 2021. Because like this took 2020 steps to get here, and then one step to get divisible by 2021. So the sum is 2021 steps to get to a multiple of 2021 or 2021 minus 1. So after getting 2020, we can get to this. And then now, from here, now if we apply the second operation to this once, because we can factor out this exponent of 2. Sorry, I meant multiply by 2. And again, now, like, just by the same argument as before, this is at least 2. This is less equals 2. And this is less equals 2021. So, effectively, the above inequalities allow us to argue that this is the following thing is true. And now, since these are both So my bad. You have to do this 20 times, by the way, because like each time we're multiplying the exponent by you're multiplying the exponent by one factor. So you're adding you're increasing the exponent by like one multiple. Yeah. Yeah. So first we multiply the exponent by 2021 each time. So we have to do that 20 times to get from 0 2021 to the power of 1 to 0 21 to 21 to the power of 2021. So this takes 2021 times g of 2021 state 0 2021 steps. And now this is like so it takes 2021 squared steps. And now all that's remaining is to get to the initial state. So initial state is to get to 2020. And okay, you can just find a way to do this fast. I think like a fairly fast way to do this is like 1, 2, 4, 20, 100. Like as someone said earlier, and then from 100 you can just go to 100 times 101, which will give you like 10100, which this is equal to 5 times 2020. So actually in 5 steps we can get to 2020. So this gives a bound of 5 plus 2021 squared, which is like definitely less than 10 to the power of 10. And now I'll just show the last like one more observation that will help us a lot. So the final thing so we can use binary on we can use binary like within this A and B itself. So I'll just show how this is done. So say n equals 2 to the n1 plus 2 to the n2 to 2 to the nk. So let me show like how we can use this binary representation with coupled with the g of AB lemmas that we have to make something even faster. So first, so the first step is so what we want to do is the following. So first we have to get to m, of course. Like without getting to m, like nothing is possible. But so we'll actually look at we have to get to x first, sorry, not m. We have to get x first, or x minus 1, because that's the initial condition, but we'll forget about that. We'll just say we have x minus 1. And then say we want to get an exponent of n. So we use the binary thing on b, which is like, so we want to multiply x with b minus 1. So we actually use binary on that b. So to get to g of 0 n, you do it the following way. So first, we have to go to g of. First, we need to get a factor of 2 to the n1 in there, because like we need some like initial starting point. So say we have like 2 to the n1 minus 1, as in like a factor of x to the 2 to the n1 minus 1. And just by what we had done before, you can do this fairly fast. So if you have g of 2 to the n1 minus 1, comma, n, then we do the following steps. So first, start with So g of 0, 2 is equal to g of 1, 2 is equal to 2. And the reason for this is that if we start with x minus 1, we can go from x minus 1 to x times x minus 1 times x squared to like, sorry, my bad. This to x times x minus 1 times x plus 1. So this way, in 2 steps, we can get here. And you cannot do any better. Or it doesn't matter if you do better or not, because like this is pretty good. It's like less equals 2. You cannot do this in 1 step. You can just try everything to show this, but yeah. And then so from this thing being less equal to 2, we do the following. So this is by the above thing that we have. And also, so the basic idea is that like to double the exponent, it takes 2 operations. And to like add 1 to the exponent, it takes 1 operation. So now, starting from like g of 1, 2, we have to double we have to double this thing n1 times n1 minus 1 times, sorry, to get to n1. And then again, we have to like increment by 1 some number of times while we're doubling, because like the idea is that we like double. By the way, these are in like decreasing order. The exponents are in decreasing order. So as we build up, like we just interleave the multiplications by like adding by 1. So what I mean by that is like if we want to get to like 2 to the 5 plus 2 to the 3 plus 2 to the 1, you first go 2 to the 1, then you add 1. Sorry, you go not that. You go 2 squared plus 1. So you go, okay, my bad. So you start with 1, you double twice to get to 2 squared. Then you add 1. Then you double again. Then you add you double again. Then you just keep building this up. You build up 1 bit by 1 bit. So like, yeah, so you just build this up like iteratively. It's like roughly just like this. Oh, I guess I'll just show the thing. So it's like 1, then you go 2 to the power of 4, then you add 1. Okay, sorry, that's not right. But yeah, basically like while you're doubling, like you add 1 each time that you need to create a new bit in that position. And as you do this, you can just like build it up in that many steps. So is that clear? Do you guys like need me to like work out this example explicitly, or like do you understand how?
Yeah, I think I understand.
Okay, cool. So yeah, basically like you add 1 in the right locations to build up each bit by itself. So now, from 1, 2, you can get to like we can get something comma m just by doing this like what we had done before. And of course, like if you just look through what happens in the algorithm, I'm just like sketching the solution out because we're like a little low on time. But if you just work through like the algorithm as you do it, you'll find that like when you multiply, when you double the exponent, you double both exponents together. So you double things 2 to the n1 minus 1 times, and then you add 1 some number of times. So then you get to this. You get to this stage where we have a multiple of like x to the power of 2 to the n1 minus 1 times x to the power of m minus 1. So this is like less than or equal to 2 times n1 minus 1 plus m minus 1 plus 2, because the 2 is just for the initial step, like the initial this thing. So this is like clearly like both of these, each of these factors is clearly less than log m. Sorry, not m. I meant k, because like the k here is the number of bits, and this is actually n in our notation. So what this means is that like now we have g of 2 to the n minus 1 minus 1 comma n is less than or equal to this, and n1 is less than log 2 of n clearly, and k is clearly also less than log 2. And if you just expand, this is equal to 2n1 plus k minus 1, which is less than 3 log 2 of n. And now
Niyanth,
this is like,
maybe we can try to wrap up.
oh yeah, for sure. Just as I was saying, just to finish up, this factor of 3 log 2 of n is just less than like 3 times whatever, 3 times log 2021 to the power 2021. If you expand now, and then you use the fact that we can get to 20 in 5 steps, and you add, you'll find that the number of operations you need is like around 70,000. So like this gives you around 70,000 operations. And this is like a huge improvement over like the 2021 to the power of 2021 to the power of 2021 steps that we had initially by just like multiplying iteratively. So basically, like, moral of the story is that like in a lot of situations in practice, and like for example, as we saw today with like exponentiation, binary exponentiation is one thing. This problem, like we saw that the idea taken to an extreme, but in a lot of situations, like it helps to consider like having the problem, solving the two halves, and then putting it back together. And that idea, if you study more like computer science in the future, that idea is something that you're going to see time and time again. So yeah, that's divide and conquer. And I hope you enjoyed the talk.
Yeah, I have one.
Yeah, thanks a lot for the talk. That was quite interesting.
Thank you for coming.
I have one.
Wow, thanks a lot for coming here and giving that talk. That was amazing from start to end. Yeah, I mean, I really don't know what to say. That was very new for us. Usually we have Olympiad topics, so that was amazing. Yeah, thanks again for coming.
Glad to hear.